Welcome to lecture 34 of MCS 471 on numerical analysis, and today on finite differences applied to boundary value problems. So boundary value problems are ordinary differential equations where we attach conditions on the boundaries. So we introduced boundary value problems, two-point boundary value problems in the last lecture where we applied shooting. Today we will reduce these two-point boundary value problems to linear systems and actually also nonlinear systems. So we will end with an application of Newton's method in several variables. So last time we already made the important distinction between linear and nonlinear boundary value problems. In the context of linear algebra, we can work with eigenvalue problems, and eigenvalue problems are very useful to solve boundary value problems with a parameter in them. So these are called characteristic value problems. So, but first we will introduce finite differences applied to linear boundary value problems. So we distinguish between two main types of boundary value conditions. We call them Dirichlet and Neumann conditions. Here is the introduction to our problem again. We have a standard notation, so we define our second order differential equation with a right-hand side function that depends, so the function f, the right-hand side, depends on an independent variable x, a dependent variable y, and then its first derivative. And we consider a bounded interval, left bound A, right bound B. Now, in the derivation of the boundary conditions, watch for the primes. So we distinguish between boundary values where we give conditions on the positions at the endpoints, and Neumann conditions impose conditions on the velocities, on the slopes, if one thinks geometrically. So thinking geometrically, last time we imposed, we proposed the shooting method. The shooting method reduces a boundary value problem to an initial value problem. So if we look at a Dirichlet problem, we are missing the first derivative to run this problem as an initial value problem. So we guess some good slope of the trajectory or some initial velocity, and we use that guess to solve an initial value problem, and then we check how good our guess was by checking the endpoint. And that reduces to an equation, to solving of a nonlinear equation for which we can use parabolic interpolation after linear interpolation. So you can visualize, so the name shooting comes from the interpretation where our velocity, our initial velocity, is the slope of a gun, of a cannon, that we adjust in order to reach a certain target. Also, so that's the Dirichlet condition. The Neumann conditions can be visualized as follows in the context of shooting. We consider a gun mounted on a tank of a fixed slope, of a fixed orientation. So we have the orientation, we have the derivative at the initial derivative, we have it given. So what we then don't know is the initial position. So we move our tank forward or backward in order to reach the end velocity, the end slope at the end of the slope at the end of the trajectory. So there are geometric interpretations. So Dirichlet and Neumann are two pure types of boundary conditions. We have two more. We can provide the initial velocity, but then not the initial position. And the mixture is then that we provide the end position. So you are sitting in your tank with a fixed slope of your gun, and then you have to arrive forward and backward in order to reach a certain position at the end. So the other mixed condition is where you have an initial position given and also an end velocity. All right, so this is the setup. So let us look at an example that will make the importance of linear and nonlinear classification clear. So we have a linear boundary value problem. Let me underline this. What does the linear mean? Well, the linear means that the right-hand side consists of a constant times the unknown y function. So the y function appears all by itself. It's not raised to some power. It is not encapsulated. It's not the argument of a nonlinear function. So the right-hand side is very simple. Now, we know from our test equation, so y prime equals y, that exponentials are to be expected. And our class of functions consists also of exponentials, where the argument of the exponential involves the constant 2, because after taking two derivatives and applying the chain rule, we have the constant 4 appearing. So it's very straightforward to check that the exponential of 2 times x is a solution of this boundary value problem. And we have a whole family. So we have a two-dimensional family of solutions. Why again 2? Because we are working with second-order problems. So when you multiply -2 twice by itself, so you do these derivatives twice, then -2 times -2 is 4. So the exponential of -2 is an other solution, but it doesn't end there, because any linear combination of these two solutions is also a solution. And we can fix one particular element in this family of solutions by imposing the boundary conditions. Forcing that at the beginning we have 1 as the first position and 3 at the other position at the end interval allows us to compute symbolically here the coefficients in the linear combination. So we have computed one particular solution of this linear boundary value problem, the particular solution corresponding to the boundary conditions. Notice that last time we did a weighted combination, but the C1 plus C2 appears also here in the denominator coefficients. All right, so this is a great example. We do have an exact solution, very good to benchmark our techniques, the new techniques that will come. So it's always good when we introduce a new technique to try this out on problems where we know the solution already. All right, then. What is the method? The method is the method of finite differences. So it's a numerical method. When we apply a numerical method, we approximate a function by points. So the points here are equally spaced out. So for simplicity, we divide the interval 0, 1 in 4 equal pieces. We have 5x values. So here it's very nice to start counting again from 0. And n here, the number of subintervals is 4, and that also determines then the step size h as 1 over n. Very convenient. We have the boundary values. So the boundary values are here of the boundary conditions are Dirichlet type. So we can immediately replace y0 by 1 and y4 by 3. So we have now 3 unknowns left, 3 unknowns that will be the unknowns in the linear system. So we apply methods of numerical differentiation. So we've seen forward differences. There are also backward differences. Here we apply forward and backward differences to approximate the second derivative. So the second derivative is the derivative of the first derivative. So we will use the forward and backward differences for the first derivative, and then take the combination, so one step forward, one step backwards if you want, and divide again by h. So this is a technique that is very convenient here. Why is it convenient? Because we have a fixed grid. So we compute the second derivative without taking any new function evaluations. So that's the importance, and we incorporate the information of 3 function values. The current function value, which is here now weighted with this combination, with this factor -2, because the current function value appeared in both the forward and the backward differences. And with this approximation for the second derivative, we then have a linear equation that involves the parameter h. A linear equation, well, actually we have 3 linear equations in the unknown approximations for the function. Let's write it out. So the picture that you have to remember here is that we have our interval 0, 1 that was divided in 4 equal parts. So we have y1, y2, and y3. I equals 1, 2, 3. So one equation for every one of the variables. And if you see this here, we can formulate the equation quite in great generality by moving the boundary values to the right-hand side. So the y0, which is 1, and the y4, which is 3, are moved to the right-hand side. So in matrix form, we have 3 equations and 3 unknowns that we can solve in great generality. So here is a Julia function that defines the system for any dimension. 2 things you have to take care for is that with Julia we start at 1, and the number of interior points is actually the dimension of your problem. So in the derivation, mathematically, in the mathematical derivation, we started to count at 0 and ended at n. So we had n-1 interior points. Here we have dimension many, so dim many interior points, but this implies that we have to divide by dim plus 1. So this is already one thing where it's a little bit inconvenient that we start at 0, but it's to make the dimension here is the dimension of the linear system. So that's why we have to be a little bit careful at, so you can verify this formula here. A is 0 in the example, B is 1, and we have to divide by 4, but we have 3 unknowns. So this is why we divide by dim plus 1. The other thing that I want to illustrate here, it's defined in a function, but notice the one line instruction to define a tridiagonal matrix. So this is very, very useful. So this is defined in a function because we want to use this for increasing dimensions or decreasing step sizes. But if you run this only once, this can be done in an interactive session, step instruction by instruction. All right, so here is how we run this for 10 points. And now, why is that important? So on this test example, we actually do have the exact value. So we can compute the exact error, or the error of our approximation correctly. We don't have to estimate the errors, but you can see how the computed error is actually meeting the expectations. So the H is close to 1/10, so the finite difference approximations are quadratic. So we actually expected 10 to the power minus 2 as the error, but the problem is very nice. So there are constants there depending on the shape of the functions, and you can see that we have 3 to 4 decimal places correct in our already with 10 internal points. First exercise, change it. So here we have another, to help you making those exercises, here is the summary. We have our parameter is the dimension of the linear system. So the dimension of the linear system, if you work with the number of intervals, then the dimension is n minus 1. But we have n plus 1 points, but we have already known in the Dirichlet problem the beginning point and the end point. Our second example is left off as an exercise, but here you can also compute the exact solution by integrating twice. You integrate the 6 times x twice, and you will see that the exact solution is a quadratic in x with 2 unknown coefficients. So the constant will be 0 because of the value here, and you will use the other condition to find the constant with x. So set up the linear system now with 5 intervals. So the spacing is 0.2. And then, so do this first quite slowly in great detail and solve this system comparing to the exact solution, which is here a quadratic. Now, how good is the computed approximation? Again, compare with the h square. So the big O is the expected order of the error. So solving a linear system, and the linear systems are diagonally dominant, so they are well structured. Here you can also see how iterative methods are very useful. So our dimensions will remain small, and we will keep on using the backslash operator. But if you want really very accurate approximations, then iterative methods will be very appropriate. All right, so let's do this now also for Neumann conditions. So the method will be entirely the same, but we have to handle the boundary conditions differently. So Neumann conditions are, so this is a condition where you have noticed the primes. So, and then the problem is then with n intervals is then a problem with n plus 1 unknowns. So we can no longer, so originally it is a problem with the unknowns on the boundary, but we still will have to incorporate the boundary values. See how we do this. So the tridiagonal system comes from the finite difference approximation, where we combined forward and backward differences. When we expand the general equation for all the unknown variables here, we end up with 5 equations in 7 unknowns, where we have 2 unknowns which are very special. So one of them is actually so special that we have a negative subscript, and then we also have y5. So these are points that are actually outside our interval. So we have the interval of interest between 0 and 1 here. How do we find values? Well, we apply the boundary conditions using central differences. So central differences do one step forward, one step backward. And here central differences are extremely convenient on the grid, because if we are at y naught, at the x naught, at the left of the interval, then we see that very naturally the y1 and the y minus 1 comes in. So we can rewrite this leftmost initial condition, so the y minus 1, in function of the unknown and the known derivative. So when the h is small enough, like here, we work with 6 decimal places. If the h is also just as small, then we can assume the equality when we do the substitution. So here we do not replace our boundary values for one of the values, for one of the grid values, but we replace, we kind of eliminate the value using other unknowns. We do the same for the rightmost. We also consider central differences, and we have then an equation that allows us to eliminate the outside point. So y5 is actually at the outside of our interval of interest. So we eliminate it, and we are then also using this boundary condition. So this is a pure problem. In a mixed type of problems, you will only have to do the central difference approximation once if it is a mixed type boundary value problem. All right, let us continue. So if we write out the equations, and here I probably skipped a step. So if you are wondering why that system comes up, go back a slide and look at the 5 equations in the 7 unknowns, which is now a system of 5 equations and 5 unknowns. It's a tridiagonal structure, but except for the first row and the last row, where we have these red letters, these red numbers coming in from the central differences applied to the outside, or to the values outside the interval. And we can write it in full generality, where also here the boundary value conditions, the slopes at the boundary, are incorporated in the right-hand sides. Let's solve it in generality. So let me point out what is the difference in the setup. So here now we divide by the dimension -1. The dimension is now in our linear algebra problems. The dimension is the number of equations, the number of variables in our linear system. So we have the dimension now goes down opposed to up. So test this for a test interval 0, 1, where now we are having, when we divide in 4, we are having 5 unknowns. So we have 5 unknowns. So to compute the h, we have to do 1/4. So the 5 becomes a 4. And the other thing I want to point out, again, that's nothing new, but if you ever have to define tridiagonal matrices, it is kind of going quite fast. Okay, so perhaps I should have indicated the difference here. So the difference is that in the last setup, you may have wondered already why there was an E and an F when they are both the same vectors of ones. Well, it was kind of to model the allowing for different upper diagonal and lower diagonal elements. So the F and the E are now different in their beginning, in their end. All right. We were computing also here most likely exponentials in our test problem. So our function goes up. What we compute are the blue dots. The plotted is the piecewise linear approximation. With 20 points, then our piecewise linear approximation starts to get much more fluid. And if we do this for 100 points, then we have a nice shape of the function. How good is the approximation? Well, we can check. So even now, if for this problem, there probably was not an exact solution, but we can compute, we can check the boundary value. So this is with the Neumann problem, where you feel a little bit less at ease, because we do have the incoming slopes and the outgoing slopes. So what you expect is that if you were to approximate the slopes using divided differences again, then as the dimensions creep up, your approximations improve. And indeed, so we see that our approximations, which are linear approximations, are corresponding with the dimension. So the 1/4 dimension is still the h, that's the order. So we have 3 decimal places as we get into the 100s. So that is a measure, that is an estimate for the accuracy. So summarizing, with Neumann conditions, we are given slopes at the beginning and at the end. We are dividing in n intervals. So now we have n plus 1 points. So which we adjust if we are fixing the dimension at n, we are dividing by n minus 1 when we compute the h. All right, we consider now the same equation as exercise 1. So if we did exercise 1, then we integrated twice to get the exact solution. But now, in order to find the coefficients of the exact solution, we will see that the middle coefficient will be 0 because the derivative is 0. So we start with a 0 slope. We start horizontally in the orientation of our canon. We have to solve for the interior points, but also now for the position. So that is another another way to see why actually we are having 2 more additional unknowns. So the same with the exercise 1. Also try, if you are having the exact solution, see the order. See if you also are having here observing that the error is quadratic in the step size. Great. I have in this lecture 20 minutes left. So 10 minutes for 2 extensions. So the essence of the lecture has actually passed now. Let's look to more interesting problems. Let's look to characteristic value problems, which apply to solving boundary values with a parameter. And why are we doing this? Well, we can reduce this to an eigenvalue problem. So eigen, if you don't want to use that word, a synonymous word is characteristic. So the eigenvalues are the characteristic values. So we take a 2-point boundary value problem. And like the pendulum, these 2-point boundary value problems admit periodic solutions. So it is still a linear problem, but there is a parameter there. And the parameter appears as a square because we want a positive number. So it's the k to the power 2 forces it to be a positive number. So we have a general solution, and kind of very interestingly, the parameter k will determine the frequency of the periodicity. We have 2 parameters, and the parameters a and b, they come from the boundary values. So let's see that. So let's solve the problem. So symbolically, we can impose the 2 boundary conditions, and then we see that the cosine drops out. So our solution is a sine function with various frequencies, and the frequencies are multiples of pi. So that's actually the key to the solution. So the parameter k shows up also in the solutions. So this is a nice problem for which we can write down the shape of any symbolic solution. So this is a parametric solution where the number of sine functions that are appearing, or the type of sine functions, is determined by the parameter in the problem, the parameter k. So what are these solutions? Well, there are waves. So here you see the first three basis functions. So the blue sine function, which makes half a period. So the red one is a sine function that goes between 0 and 1, attains all the values that the sine function can obtain. And the later members in this family will oscillate much more rapidly. Let us compute these values now numerically. So in a way, this problem is solved. It's a great test problem because we know what we have to compute. It's plotted here. So we will show how to reduce this problem to an eigenvalue from applying finite differences again. So in a way, this is an application to reinforce the formula for the second derivative. And we have done this already 2 times, so we immediately write down the general formula, keeping in mind the grid. So let's do this still one time a little bit slowly, where we have 3 internal points that we have to determine. So we write down the general equation, but now it turns out that we have this parameter sitting in. So we have 3 equations in 3 unknowns after eliminating the 2 boundary conditions. So the boundary conditions now the endpoints of the interval, so the y0 and the y4. So these are the 3 equations that depend on 2 letters. So h is actually also a parameter, but it's a fixed step size. So here I did not substitute it, but it has the value 1/4. So it is a number that comes in there because we have the 4 intervals. K is our parameter that we will use in the formulation of our solutions. And here it is. So it is a system with a parameter in there, and the parameter appears in a very specific way, in the way in which we recognize the eigenvalue problems. So the eigenvalues will give the specific values for the parameter. So here you see that the lambda is this h squared times k squared, but knowing that the h is fixed, so 1/4 in the example, that means that the solutions that occur here depend on the grid, on the spacing, on the number of intervals that we picked. And why is that convenient? Well, the number of interior points is actually the size of the eigenvectors. And the eigenvectors satisfy the equations. So if you solve the eigenvalue problem, you compute the parameters, the type of waves that you can make in your solution, but you also compute all the approximations for the basis functions. So this is, by the way, I should point this out earlier. Why is this so nice? With a linear problem, we have a family that's parameterized by 2. Here we have a problem where the dimension can be extending to whatever value your computer can hold. So there are Julia programs in the Jupyter notebook posted for this lecture. Here is the plot that is made with in the Jupyter notebook, where we are using 15 interior points. You can see that the first wave is approximated quite nicely. There are some, if you look very carefully, there are some pieces there, so it still is not completely smooth. You see that the 15 with the piecewise linear approximation is a little bit too coarse, but we approximate the shape of these first three basis functions rather neatly. There are two things that you need to do in the plot. We need to add in the boundary values again, so the conditions that at the end we have zeros. Also, eigenvectors are determined only up to multiplication with a non-zero constant. So the Jupyter notebook will scale the eigenvectors so that the largest element in absolute value is 1. So this is a different norm. So the programs that compute the eigenvalues and eigenvectors typically use the 2 norm. But for this application, the 1 norm for the eigenvectors is more appropriate. All right, one more exercise. So the exercise is a little bit more complicated than, or actually the exercise remains the same, but the discretization will involve the x. So we will no longer get the same explicit solutions that we are getting for the first exercise, for the example. So this is why this is numerically a more interesting problem. So set it up in generality. So here it stops with h equals 1/4 and check the accuracy, what the accuracy that you may expect from this solution. But don't hold yourselves back if you want to go for larger dimensions. So this is a problem that essentially can also be solved by paper and pencil. But if you set it up in great generality, you can solve it for any dimension. And look at the periodic solutions, or if they are periodic at all. All right, in the last 8 minutes, I will illustrate the application to a nonlinear boundary value problem, which allows us again to enforce the application of the finite difference method, and also go back to Newton's method in several variables. And here in a purely numerical context. So we did the Newton's method in a more symbolic context by intersecting equations. But here we will see how Newton's method is very good in a nonlinear setting. So you see the nonlinearity occurring, how this will lead to a nonlinear system. So I have placed the nonlinear term, so the power 2, right up front in the general equation. So we will formulate our problem first for 3 equations and 3 unknowns. Why is that? For 3 equations, because it then all fits nicely on one slide. And if we have the pattern for 3 equations, we know the general pattern. So here it is. So we have the 3 unknowns that all satisfy the same equation. It's a system of 3 quadratic equations, but it's almost a linear equation. And why is that? Because of the coefficient h to the power 2. So this is a nonlinear problem, but it is very, very mildly nonlinear. And that will help us in solving it. Newton's method is a local method and converges quadratically. We will experience this as well. So we are having at the bottom here a system of 3 quadratic equations in 3 unknowns. The boundary values are already eliminated. So you recognize the 1 and the 4, and we have the 3 values there. If we apply Newton's method, we need to compute the Jacobian matrix, so all the partial derivatives. So the Jacobian matrix is a tridiagonal matrix. So here again, it's also a diagonally dominant matrix. Well, yes, so we have the factor 2 sitting in there. And in Newton's methods, it's a long time ago, we solve a linear system evaluating the Jacobian matrix at the current approximation, which is now a vector of 3 values, and we also evaluate the right-hand side. So we do this 2-step process. Why we do this? Because the right-hand side gives us an estimate for the backward error, and the delta y gives us an estimate for the forward error. Problem that we still have to solve, where to start. Well, we can always start at 0, but notice here that this problem is close to being a linear system. So the h, I mean, now it's a large number because we are working only with 4 intervals. But typically it's 10 to the power minus 4, and then for h, then h squared is 10 to the power minus 8. So we can drop that term, and then we get a nice linear system, a nice diagonally dominant linear system that has a unique solution, and that solution we will use. So we have to solve one linear system at the beginning before we start Newton's method. We have one linear system that will actually give us a good start solution. Here is the output. So why is this a good start solution? Well, the first residual is 10 to the power minus 2. So Newton's method converges quadratically, and that's the thing that I also want to point out here. So we read the numbers backwards in this course. So we look at the exponents. So we go from minus 1, minus 2 to minus 5, better than minus 4, and then to minus 11, better than minus 10. So we get in 5 steps, 10 decimal places of our solution. And the accuracy here is more than enough, because this was done with a step size of 10 to the power. So I was using 40 intervals. So the accuracy of the approximation here should be correlated, should be related to the value of h of your discretization. All right. Before we end, let's do one other exercise. So set up the nonlinear system here in generality, or first do it indeed for 4 intervals, and run Newton's method on the system. So there is a program, a Julia program, that has several Julia functions, so that you have to adjust. Once you see the pattern of the nonlinear equations, you can formulate the Jacobian. There are 2 functions that you have to modify. One to evaluate the right-hand side, to evaluate the function, and another to evaluate the Jacobian matrix. And then run Newton's method on this problem.